It's a pleasure to have. It's a pleasure to have Jonathan here, so who visits us from Philadelphia. And yeah, he will tell us something about disorder averaging and its UV contents or this content. Yeah. Thank you.
Okay. So first, let me say thanks very much for the invitation to. Okay.
Well, the opposite would be better.
Is that too dark? Yeah. Okay. So first, let me say thanks very much for the invitation to come and give a talk. It's especially great, considering all the Zoom stuff that's going on.
Go on.
Yeah. Okay. So what I'm going to tell you about today is is based on a project which will hopefully appear soon.
I'm sorry, I have to share your screen. So,
okay.
Because
no
that's
problem.
something we should do.
It's okay now?
Yeah, it's okay.
Oh, hi, Katrin. No, okay. So it's based on a paper that hasn't appeared yet because we're still trying to sort out some of the interpretational issues, but hopefully it'll be out in optimistically in a couple of weeks or so.
I'm sorry.
It's
Can you click and just?
yeah, I just do it.
And so it's probably not working, so it's probably just.
Okay. Okay. Yeah. So it's based on a paper which will hopefully be out soon. So it's with Andrew Turner, who's a postdoc in the UPenn group, and Xingyang Yu, who's actually a graduate student at NYU, but he's in the Philadelphia area for various reasons. So he's done a lot of work on like 2D CFTs, in particular relations to like special holonomial manifolds like spin7. Deeper into probing this. He's applying for jobs this year, I think. So anyway, so it's been a really fun collaboration with them. It's also kind of tangentially based on something which appeared basically in December of last year. I'll mention it, although it's not going to be my main focus. It's with again with Andrew Turner at the end there, Vijay Balasubramanian, who's done a lot of work on ADCFT, and Elliot Lapellis, who's an experimentalist at Atlas. So slightly different focus for this paper, but one of the things we were aiming to do is see if we could take these original ideas and connect them to here. And to some extent it worked, and to some extent it didn't. So I'll give you a flavor of this paper, but I'll mainly focus on this one. Okay, good. So first I'm going to try and provide some motivation for why we're going to be doing these things. In particular, disorder averaging in the context of conformal field theories. And just to kind of set the stage, the idea is we're going to be computing correlation functions in a quantum field theory. Now, when we do this, we make reference to various coupling constants that we just fix as parameters of the theory. What we're going to be doing is considering an ensemble average over those correlation functions. So in other words, we imagine that we have not one theory with particular fixed values of parameters. We'll compute the correlators with fixed parameters, and then we'll do a further averaging with respect to some probability distribution, P of lambda. And this is shown up in various contexts, especially in the ADCFT correspondence. It's, of course, a very old idea in the condensed matter literature as well. But one of the big questions in this context is, well, does this really make sense in the context of ADCFT? Does it really lift to something that has a UV completion? And that's really where my focus is going to be. So I'll try to illustrate the sense in which we can do this and the sense in which we cannot do this via some examples. And then I'll summarize and tell you about future directions. Okay, so here, let me begin with some motivation. So a famous thing is that recently much progress has been claimed by combining kind of two things. One is holography, and one is effective field theory. And one of the things that has come out of this is basically just by analyzing the gravitational path integral, it's claimed that in many cases you can extract lots of important information literally about black holes and so on, using just statements that you can see already in the effective field theory. Now this is, at least to a string theorist, this is a kind of a surprising claim, because the whole essential point of holography is, first of all, that we have lots of examples that come from string constructions. These are basically the only ones where I would say we have reliable construction of holography in the first place. And second of all, we already know in that context that there can often be non-trivial effects where effects in the ultraviolet can creep into the infrared and vice versa. So the claim that you can kind of completely decouple or sequester things that are happening in the ultraviolet, just talk about the ADCFT correspondence with no reference to string theory, is already a surprising claim, at least from the perspective of string theory. Nevertheless, you know, if it works, and you know, what can you say? So there's been lots of claims about how wonderful this all is. I'm happy to explain more about what I think about these claims, but I don't want to turn this into a rant. Let's just get into ADCFT. Recall that what we typically—
Excuse me, can I ask a question? A quick
Yes,
one?
please.
The remark about UV completeness not necessary is very surprising for me to hear. Can you say a few more words about this, please?
Right. So for example, the whole point is that what's being done is at the level of gravitational path integral. And if you like, they're taking it just face value, the idea of doing quantum gravity using the Euclidean formulation of gravity, and just saying this is how it's going to work. Now, just at the level of UV completeness, you would ask, well, what about all the higher derivative corrections to that statement? Just at the level of the action in whatever dimension you're talking about. The point is that it's claimed that a lot of the things that we're doing are just effective field theory statements. And so in that sense, if you're being an effective field theorist, you're only working at low energies. And so why should you care about the UV completeness of the theory? You might say, well, there's some mild constraint like coefficients have to be positive or something like that, but that's the extent at which UV completeness might enter the story. So the point is kind of, they say, I don't need the string theory embedding to kind of make a lot of the claims. So I don't know if that answers your question, Irving.
Almost, but not entirely, because if you keep pushing to higher derivatives, you will require, again, consistency. And in effect, that means UV completeness in disguise, really. It's just that
Absolutely. You are— I'm very sympathetic to your point of view.
Yeah, okay.
Whenever I hear these talks on this thing, I ask basically the same question as you do, which is, how can you make these claims without a UV, you know, even saying something like, tell me something more about the higher derivative corrections. But kind of the essential claims are that it doesn't matter because I'm talking about infrared effects that don't really require me to get in.
Okay, thank you.
Yeah. So I'm very sympathetic to the point that you're raising. So you could just, I mean, on the other hand, effective field theory is great. I mean, I don't have to know about quantum gravity to compute things in the standard model. So maybe it's like that. Okay, so recall in ADCFT, what we do is we have some boundary conformal field theory, and we have anti-de Sitter space in one more dimension in the bulk. And this is, you know, been a real, you know, triumph in the last however many years now. And so it's great, and there's basically a very large dictionary that's been developed just at the level of what we call a classic ADCFT. So obviously I can't review everything, but the idea is we have some large N theory, some large N parameter, and this kind of sets for us what we mean by having a semi-classical gravitational field. So I can't get into the details here, but let me just sketch some of how it goes. We imagine we have, say, bulk fields. They have some asymptotic boundary values. And then this, roughly speaking, sets what we call parameters in the conformal field theory that lives on the boundary. And so if I compute things involving, say, particular gravitational path integral with prescribed boundary conditions, that's what this symbol here means, then I can match it to something that I'm doing in terms of generating correlation functions over in the conformal field theory. And here I'm working in Euclidean signature. And so this prescription basically came out by Gubser, Klebanov, and Polyakov very shortly after ADCFT was down, and at this point, it's a vast industry, and you know, continues to this day. Okay, so it's great. This is obviously in Euclidean signature because I need the minus action. But okay, this is a big industry, but it also raises various puzzles that you can ask. So here's what I'll refer to as the factorization puzzle, and this is where things kind of look deceptively simple. Consider a bunch of multiple CFTs, each with their own parameters. And for each one of them, we could say, okay, great, it has its own kind of gravitational dual. So I've tried to draw that as this little, so each one of these is a little ADS. Now, if we go over to the gravitational side, this is where things start to get a little bit strange. You can look for configurations, again, in the semi-classical Euclidean gravity. You would say, well, could there be configurations which connect the different pieces? This is not as easy to exclude as you might think. And so what's going on here is it looks like somehow these two seemingly decoupled CFTs are now interacting with each other gravitationally. So from a field theory perspective, it sounds bizarre because I can talk about a CFT as a UV complete theory by itself. Where is this bulk gravitational stuff coming into the game? You can ask the same question on the gravitational side. Suppose you have an ADS and it has multiple boundaries. So if we play the game this way, then the breakdown is occurring in terms of this partition function, or this inequivalence of the partition functions. We can try and compute these decoupled CFTs. We'll just get some product if we do it naively on the field theory side. But if we do it on the gravitational side, clearly, they're all kind of mixing in some way, so we don't expect that it factorizes. So this is what's sometimes referred to as a factorization puzzle, and it can be made more precise in various kinds of toy models, especially in low dimensional gravity settings, but it seems to be like a general conceptual issue you might worry about. Okay, so one proposal for how to deal with this is that really what's going on is we're not really talking about a single CFT, but really some kind of ensemble average. So from the gravitational point of view, the idea is that, well, let's consider the Hartle-Hawking wave function as defined by Hartle-Hawking defined it, like imagine you have the no boundary state, and then we kind of cut open the path integral, and then we have some number of boundaries with some prescribed boundary conditions. Then we can compute a wave function like this. And what's going on is that we're just writing down like a wave function for this universe, and we're just getting some probabilities to have various kinds of components with various kinds of coupling constants and boundary conditions coming out. So what this would mean in the context of ADS-CFT is we're talking about some kind of ensemble averaging over a CFT. So here we say we have a fixed parameter lambda, and then we consider a probability distribution over those lambdas. So these are all basically, just bottom-up consistency, self-consistency conditions that we might want to talk about in this context. Okay, so in particular, in the context of ADS-CFT, we have these ensemble averages. And Marolf and Maxfield explained that, continuing again with this bottom-up type reasoning, that actually this kind of thing is connected with the idea of kind of the birth and death of baby universes. And the reason is that if you imagine slicing open, like, this is some time evolution, you imagine slicing it open, and then there's some notion of different kinds of parameters. So this goes back to this work of Coleman, where he was writing down alpha states and kind of probabilities over possible coupling constants. And the point was that there was this averaging over wormhole configurations, which kind of forced there to be some kind of coupling constant. So it's a fairly, I would say, confusing set of ideas. And in fact, McNamara and Vafa, motivated more by swampland considerations and string theory considerations, pointed out that really, in the context of string theory, this doesn't look like it makes that much sense if you want to have really high dimensional gravity with these kinds of baby universes with ensembles over couplings. What's the reason for that? Well, in all string theory constructions, coupling constants descend from dynamical fields like moduli, and there's no sense in which they can kind of be frozen to kind of position independent values, which is really crucial for this kind of baby universe type consideration. They phrased it in slightly fancier language in terms of this so-called swampland coborism conjecture, but basically they were at some level just pointing out that there's kind of a tension between what the bottom-up holography folks want to talk about and what you might want to do as a string theorist. So it's a puzzle at that level. So there's kind of a tension going on, and the question is how to resolve the tension, or who is right, who is wrong, is anybody right, is everybody wrong? Okay, so the big assumption in all of this is, as I already mentioned, that all this makes sense in the infrared, so no UV completion is necessary. So if that's really true, it shouldn't matter how I UV complete the system, right? So I'll pick my favorite perverse UV completion and then see if I get the correct infrared behavior that they want to talk about, and then we can just check whether everything works as claimed. So that's what I'll try to do. So indeed, what I'm going to try and do is explain to you how to build infrared ensemble averages of the kind I just talked about. We're going to write down some CFT, some ensemble average over the couplings, and we're just going to ask, does any of this break down, either the infrared, the ultraviolet, and so on? And we'll be able to do it because we'll try and write down some explicit examples. Okay, so punchline number one, indeed, we are able to produce ensemble averages and string compactifications. I'll tell you how to do that. But punchline number two, it comes with a finite number. I'll call it MUV, and I'll tell you more about what that is in a little bit. But what it means is that if you ever try to sample any kind of bulk gravitational physical object more than that number of times, this is, if you like, an entropic effect, which is visible at infrared energy scales. In particular, if you have a macroscopic black hole, which is sufficiently big, and you're sampling it enough times, this is a thing that you could spot if you're talking about the ensemble average interpretation. It's a thing you could spot in the infrared with just due to entropic effects. So I'll explain exactly how we can see this breakdown occur. But the point is that it's an ultraviolet effect, but it's something that is visible in the infrared from just saying I wish to sample a huge number of times. So it directly goes to the core claim that I can get rid of UV physics completely. Okay. So now I'm going to move on to explaining how disorder averaging goes in these in various ways. Are there any questions about what I'm going to try and do? Okay. Okay, so let me explain a little bit more about how disorder averaging goes. Consider a quantum field theory with some parameters. And I already said this in words, but let me just spell it out. We imagine defining this overline by basically computing correlation functions with respect to some fixed value of parameters, and then doing a further averaging over this. And in the context of field theory, it's often very convenient to promote these things to local sources. And why would you want to do this? Well, it provides you a notion of typicality. And it also provides you, so it's introduced, especially in the condensed matter setting, to get a suitable notion of complexity, and when you're dealing with very complicated things and you want to be able to access like the typical phase structure of this. And I'm just mentioning here like the various places it's shown up both in phenomenology and in high energy theory. Okay. So many QFTs are generated by strings. Can we generate these kind of probability distributions over, say, local sources? And also the case where it's constant. Okay, well, let me first briefly mention the case where it's position dependent. That actually turns out to be a bit easier at some kind of crude qualitative level to get right. Getting the details right of this case already is a bit challenging, and that was actually how our project started. But we realized we could actually do something a bit different using position independent ones, and that'll be my main focus. But let me first briefly mention the idea of how you get position dependent pieces to come in. Okay, so that was the paper that already appeared last year. So localizing a QFT. So the idea is in a string construction, we often have some 10-dimensional space-time, and then we have localized objects like branes where degrees of freedom are trapped or localized. So there's a sense in which gravity can kind of couple at some level. So we have all these little local branes. So like a D3 brane would fill 3 + 1 dimensions, instead of a point in the extra dimensions. And we could do this multiple times all over the place. Okay. So if we were interested in, say, the standard model being here or some other kind of quantum field theory interested being here, we could ask, this thing has some parameters. Where did those parameters came from? They came from, if you like, the remnants of the 10-dimensional metric, the bulk descending down onto this set. So what can you do? You can take the full Hilbert space of the system and do a partial trace over everything other than the visible sector. So I'm denoting that as trace vis bar, so the complement. So there's some partial trace. This is just a quantum mechanical operation. In the sense that the Hilbert space factorizes into these little pieces, we can do this. And what we can do is we can say, okay, we have some ground state. We typically label this by a choice of coupling constant. Suppose it's a pure state like this. Matter product. But when we do the partial trace, what will happen to us generically will wind up in a mixed state. This is just a statement about entanglement, if you like, between the visible stack of branes and everything else. You'll wind up with some position dependent coupling. Now, what's the reason it's going to be position dependent generically? Well, where did I get these things from in the first place? I got them from moduli. These are coming from dynamical fields, which are being taken to heavy or not interacting very strongly with the standard model or anything like that, but they still have some position dependence in them. So generically, you get this kind of thing. And what we tried for a lot of the project was to actually take limits where you get rid of this position dependence. And none of those things really worked, I would say. And so we had to actually take a different tack to get the case of position independent. So it's a different set of ideas to get this, but I wanted to mention that this is how you go about getting the position dependent case. An outstanding open question is to kind of like now just like start computing in explicit examples what that density matrix is. But I hope you can see that I'm going to give you something that looks like a probability distribution to lead order. Okay, so now let me turn to the case of P of lambda, which is going to be my main focus. Okay, so I already mentioned baby universes and so on. Now, a really crucial point is that when you're giving birth to this baby universe, to satisfy Gauss's law for diffeomorphisms, it's very important that those coupling constants that we're talking about have no position dependence at all. Because if we introduce position dependence, we would basically be violating the analog of Gauss's law if this thing kind of asymptotically extended off forever. So there's a sense of a conserved charge, and we would violate it if we had some position dependence. So we really do mean like an absolute constant, no position dependence at all. That's where things get a bit murky, because the point is that McNamara and Vafa point out that sure, moduli are a great way to get x-dependent coupling constants, but then you will be violating Gauss's law, and birthing or giving birth to a baby universe wouldn't work in the same way. So we really want to talk about the case where it's position independent. Okay, so now I'm going to tell you the main idea and how we're going to implement it. So how do we get the coupling constants of a brane construction in the first place? So I just told you earlier that what we do is we say, well, we have some higher dimensional modes coming from the 10-dimensional metric. And then on the brane itself, we have some boundary condition for this. This is how we get our coupling. Now, what's happening is that in, say, the 3+1 dimensional world volume of the D3 brane, or whatever brane system you want to talk about, the modes, the bulk gravitational modes, are non-dynamical in 3+1 dimensions. They're dynamical in 10 dimensions, but not in 3+1. So the way we actually get the parameters of the quantum field theory that we're interested in are coming from basically setting boundary conditions for those fields at the location of the brane. So what I'm going to do is I'm going to say, okay, can I arrange it so that the internal profile of the metric on the internal dimensions has different values for those couplings, say at some point here and some point here. And what I'm going to do is I'm going to try to replicate the same quantum field theory at these 2 points in the internal directions. Okay, so it's 2 copies of the same system. So it's quantum field theory number 1 and quantum field theory number 2. I'm going to demand that they have exactly the same operators. So this will be arranged by my choice of brane construction. But I'm going to try and tune it so that they have different values of the coupling constants. Okay, so this is how I'm going to start building an ensemble basically by hand. So,
excuse me, a quick question. What branes should we be considering here?
I'll tell you in a little bit, but if you keep the example in mind, consider D3 branes. So 3+1 dimensional objects, and then the thing we would be talking about is the string theory dilaton and a profile for that here. Sorry, I guess you can't see that. A profile at lambda 1 and a profile at lambda 2.
So all this consideration will be relevant for a given brane dimension, right? I mean,
that's right. Yes. So it'll be heavily dependent on the space-time dimension I'm in, and it'll be dependent on what kind of probability distribution I'm trying to engineer.
Okay, thank you.
Yeah. So again, my construction is going to look pretty contrived, but again, the point is, it shouldn't matter to you because the claim is all about what's happening in the infrared. So no matter what kind of perverse UV completion I give you, it should not matter because we're talking about infrared physics. Okay, here we go. So to give an example, let's take n = 4 super Yang-Mills theory. Now, how do we realize that in string theory? We take a stack of D3 branes. So these fill 3+1 dimensions, and they set at a point in the 6 additional directions. So what I'm going to do to generate a set of possible values for the coupling constant, the complexified gauge coupling of the gauge theory, is I'm going to introduce a background source, a D7 brane. Okay, so when I do that, what happens? Well, it sources, if we try to write down the metric, and it introduces some stress energy. And in order to solve the supergravity equations of motion away from the stack, we have to introduce a position-dependent profile for the axiodilaton. Now, this thing descends to the complexified coupling on the stacks of D3 branes. So what are we actually engineering when we do this? It's not quite n = 4 Yang-Mills. It's n = 4 Yang-Mills plus terms that that have explicit breaking to n = 2. But these are all higher dimension operators. So as long as I stay energies where the effects of this n=2 breaking, these higher dimension operators, are very, very small. In the infrared, I should expect to have something that the leading order is described like n=4 Yang-mills. So what am I going to do? I'll pull the D3 branes away to different distances. If I want a particular value of tau1, I'll find the value of z that corresponds to. I know such a thing exists because I can solve this equation. And if I want another value, say tau2, I'll pull them, say, further away. Okay, so this is my simple-minded distribution. In this case, it would have equal weights to tau1 and tau2.
Can you elaborate on why the n=2 breaking is higher derivative?
It's not higher derivative; it's a higher dimension operator.
Oh, sorry. Okay.
Yeah. So a classic example would be like Seiberg-Witten theory. So this is like Seiberg-Witten theory, if you like, of SUM gauge or UM gauge theory with a hypermultiplet. And the mass of the hypermultiplet is controlled by how far the D3 brane is away from the D7 brane state. So in other words, what we're doing is we're saying we pull the D3 brane away from the 7 brane, the hypermultiplet gets a mass, we integrate it out, and where is that mass showing up? It's showing up in the suppression scale associated to this n=2 breaking. And so the approximation is going to be very bad if I put the D3 brane close to the D7, but it'll get really good if I pull the D3 brane far away. So that's a UV cutoff. So I shouldn't trust what I'm doing if my energies ever get close to the UV cutoff. But if I'm far away from that, then it should be okay. Okay, so let's introduce some operators. And there's a particular set of operators I want to talk about. They're kind of, if you like, the ones that I get from tracing over the stacks. So I'll call that a bold O, and it's just going to be O1 plus O2. And this is your favorite operator in this theory. So it might be like tracer field strength squared, or I don't know, whatever you like to talk about in n=4 Yang-mills. Okay, so what are we going to do? Suppose I give you my favorite operator, and suppose I give you another of your favorite operators. Let's consider the correlation function between O and O prime. The key point is that all the operator product expansions and all the correlation functions kind of close in this bold-faced subset. So again, this is not a UV complete thing, but at low energies, the operator algebra will close on these bold guys. So in other words, all the effects of being outside of this special like diagonal trace are the off-diagonal things we've already integrated out. So it won't work to arbitrary energies, but it will work at long distances. What does averaging look like in this context? Let's just compute the correlation function between bold O and bold O prime. It's a leading order. Again, there's no O1, O2 prime. Why is that? Because that's an operator over here, and that's an operator over here. How do these two stacks interact with each other? Through very massive stringy states, which we have integrated out explicitly. So if you like, you could think about this as a U2M n=4 Yang-mills theory, and then we went on the Coulomb branch, and we have a bunch of off-diagonal W bosons, which have gotten a big mass, and we've integrated them out. So this is the sense in which this is an approximation, because of course the approximation breaks, provided I go to distances where I can probe those W bosons that I integrated out. But if I remain at energies far below that, this is a good approximation. Okay. Now, how am I going to build a more complicated ensemble? Well, what I'm going to do is I'm going to say, let's say I have my favorite K values that I want to produce a distribution. So I'm going to discretize an approximation, a distribution. So what I'm going to do is I'm going to take my favorite K values, tau1, tau2, tau3 up to tau K. And what I want to do is I want to start weighting them differently, depending on how much weight I want to a particular value of the coupling constant. So if I want something that has high statistics at some particular value of the taus, I'll put a lot of stacks over here. Now, what I want to do is I want to pull them all the same distance away from the D7 brane, but I also don't want the approximation to break down. So I have to keep them separated from each other in the other directions. So what I'm going to do is use basically, so here, let me, well, okay, I guess you can't see it on Zoom links, but I'll be showing this on a slide in just a moment. So we had this Z direction that we used to build the profile for the axial Goldheim. This is where the D3 branes all live. We're going to use these directions to sequester or keep the D3 brane stacks away from each other. So even if they're at the same point in the 8-9 direction, I'll keep them at very, very different directions in the remaining extra dimensions. And so the actual mass of a string state which connects one of these D3 brain stacks to another will still be extremely high, and therefore I can still build a reliable low energy effective field. So let me say, okay, so now I can say that I can build like some number of stacks with coupling tau 1 and some number of stacks coupling tau k. What's the probability distribution? What's the probability? Well, what we've just built is a discretized probability distribution that looks like this. What's the odds that I grab a particular random value of tau, take the number that I have of a particular value of tau, and divide by the total? That's it. So just an ordinary discrete or distribution. And the total is just like the total number of things we have. So just sum over all the stacks. Okay. So what are we doing? So there's a sense in which you can't actually pin down the value of the coupling constants. There's an intrinsic thickness to every brain. And so really what we're doing is we are building up a histogram, and it has some intrinsic spread to it. That spread is kind of controlled by a UV cutoff type consideration. But the point is that we can now start approximating your favorite smooth probability distribution. Here I just picked the Gaussian with respect to tau. You could pick something else. And we're just putting everything into a finite number of bins. So we're just literally building a histogram using these kinds of things. Okay. So now I've told you how I'm going to build an approximate distribution. Now what happens if we start looking at our bold O's? Now we're summing over all the stacks. And when we do the averaging, what's it going to look like? It's going to look like a disorder average. Why is that? I have this number of copies, and I sum it with this number of weights. So you're doing exactly the same computation over and over again. And so it really will start approximating this, this averaging over the correlation function. Okay, so this is kind of the central point of the construction. So maybe I should stop here and ask if there's questions, because this is kind of the key point of everything I'm going to do is going to be giving you examples, elaborating on how to do this in practice. So any questions about the main claim?
So this approximation means that you ignore the higher order.
Correct. Yes, exactly. So I only trust what I'm doing as long as I'm at low energies compared to that scale. So the first thing I have to do as a good effective field theorist is tell you, okay, great, where does the approximation break down? So that's what I'm going to do on the next slide for the particular example we did in D3, D7. But that's going to be my main task going on. I'm going to give you a brain construction. I'll try to populate my favorite distribution, and then I'll have to identify where is the ultraviolet breakdown, and are there other ways this approximation could break down. So that's got to be my goal, to tell you, let's replace this squiggle and say, I trust this up to subleading corrections. What are those subleading corrections look like? So I'll try to answer your question. And more questions on what I'm doing or claiming. Okay. So where does this thing break down in the particular example I talked about? There's two breakdowns in the ultraviolet. One is we have to be working at energies far below kind of this W boson mass. So one of the ways is just in terms of the relative positions of the D3 brains from each other. Okay. So if I put the D3 brains too close to each other, then there's straight states, there's stringy states that are becoming very light, and I don't have a good approximation in terms of n equals 48 mils anymore. Now I have basically massless states that are coming in, and I have to pay attention to those. How can I get rid of those? I'll use the 4, 5, 6, 7 directions to move the D3 brains as far apart as I please. Okay, so there will be an intrinsic, limitation to how well I can do it, but I can improve my approximation by just pushing them a little bit further out each time. Now, there's another way that this breaks down, which is the distance between the stacks of D3 brains and the D7 brain, which I was using to generate the profile for the axial dilaton in the first place. Remember, that's how I was able to generate possible values of tau in the first place. If I didn't have the D7 brain, I could build you an incredibly boring distribution. It would be the same coupling constant everywhere, and I would have accomplished nothing. So I'm introducing this background D7 brain, but the price I pay is that if I try to produce a distribution that gets me too close, the D3 brain getting close to the D7 brain, then it's not going to work. The approximation will break because there will be a light state coming in from the D3 brane getting very close to the D7. So that's the other cutoff, this distance D3, D7. Okay, so as I already said in words, that distance between the D3 branes is tunable, but there's this thing here, the D3, D7, which means that the actual distributions I can accomplish doing this are going to be cut off. So there's going to be a tail that I always cut off. And I can start recognizing that I cut off this tail by sampling from the distribution a sufficient number of times. So if I try to build you a distribution where I just chopped off the tail, if you sample enough times, you will eventually land on the tail and you will discover that I cheated. In other words, in terms of building the honest bell curve. So we've already seen now an example of an infrared breakdown of the approximation. If I sample this thing enough times, I'm in trouble.
So in this plot, is n tot an integral on the one side of the red line?
Oh, I'll tell you more about what I mean by sampling in tot. So in tot here is just like the total number of stacks I used. So that's kind of the rough idea. You should definitely expect it to break down because at that point you're seeing the discretization of the whole distribution. In fact, the breakdown happens before in total often. So if you sample less than in total, you often will still be able to tell the difference because we're fitting things into these finite.
So it's not just the property of not taking the continuous limit, it's more severe than that.
Yeah, it's it has to do also with this like binning procedure. So I'll come back, and if you're not satisfied, then ask me again. Okay, what's the gravity dual of this thing? Well, we have a large number. So let's say we have m D3 branes at each of our stacks. We can take the Tooft limit. What does that mean? Take a large number of colors and switch the value of the string coupling to 0. And this is, famously in Malvasina's paper, you get ADS 5 times S5. But what we have here is we have a bunch of stacks, all at different locations in the internal geometry. So we don't get one ADS 5 times S5 geometry, we get a bunch of them, each with their own value of the cosmological constant. What sets that? The Tooft coupling. Again, we know this via Malvasina's original construction, which was just the near horizon limit of a single stack of D3 branes. So here I've tried to indicate what that looks like in terms of a multi-throw ADS geometry. So kind of each one of these little pointy jagged edges is supposed to be an ADS throw. But it's not too hard to actually write down the explicit metric in this case. In this particular case, we do know enough to write down the explicit metric.
Do these ADS spaces differ only by the cosmological constant?
Yes. Well, so that's in the limit where we neglect the n equals 2 breaking terms. If we include the n equals 2 breaking terms, then there's further deviations that you have to take into account. But I'm neglecting those for that part. So yeah, the only parameter I can speak about in this case is the cosmological constant, and we'll just get different values because we have this. We basically just have the dilaton, and that's it to play with.
Okay, thank you.
Okay, some more examples. So I didn't succeed yet in building you the thing that Marolf and Maxfield wanted to talk about, because they wanted to have a single ADS with this fluctuating boundaries and so on. How are we going to do that? Well, what I'll be after is finding you examples where the cosmological constant in all the ADS vacua is held fixed to the same value, and then I'll vary the other parameters of the theory. So the special thing about n equals 4 Yang Mills is there's a single parameter which preserves n equals 4, the complexified gauge coupling. If I have more elaborate gauge theories and so on, then I can tune to keep the cosmological constant the same, but I can also vary the other parameters, other marginal couplings of those CFTs to produce the desired ensemble average. So I'll explain how to do that in just a second. So now I'm going to do some examples. Okay, so the examples I picked are ones that they're just examples that we happen to know better than I'm sure we could cook up more. So the first one I'll tell you about is 4-dimensional quiver gauge theories. LST here refers to a thing called a little string theory. You should think about this as kind of like it's a kind of string theory that kind of sits above a superconformal field theory. It contains a few more degrees of freedom than a 6-dimensional superconformal field theory, but we're going to use that to build various kinds of 4D quiver gauge theories. I'll give you a 2D example and I'll put it in quotes, a 1D CFT. I should say that the vast majority of claims about these ensemble averages are usually for low dimensional systems. So usually like ADS2, CFT1, and sometimes ADS3, CFT2, but usually it's very low dimensional things. And the lore at least has been that, oh, you shouldn't, maybe it doesn't work to make these ensemble averages in higher dimensions because that's when gravity becomes rich and dynamical and so on. But maybe it works in these like low examples, low dimensional examples, because it's almost topological, and so maybe we get away with it there. So what's going to be funny about the examples I'll tell you about is we have the best success in higher dimensional examples in 4 dimensions, and we have moderate success in the lower dimensional examples for reasons I'll explain in a bit. So I'll present first kind of in order of like our competency in building a nice ensemble. So I'll tell you the best one first, and then the one that where things are slightly more shaky. And so the funny part is that this is the one that everybody talks about in terms of SYK, JT gravity, things like this. And it turns out this is we can do it, but it's a little bit shakier than the other ones. Okay, so let me do a 4D example. So let's consider a quiver gauge theory. So a little string theory on a 2 torus. So it's 6 dimensions compactified on a 2 torus. At long distances, this will turn into a 4-dimensional quiver gauge theory. In some examples of little string theories, I'm going to pick one so that the 4D quiver gauge theory, you don't have to know any details about little string theory for what I'm going to say. It's just, this is how we built it. We have a 4D quiver gauge theory. Each one of these circles is a 4D n=2 vector multiplet. So each one is an SUM vector multiplet. The little links in between each one are a 4D n=2 hypermultiplet. They're in the bifundamental representation, and around it goes. And it's known that this 4D n=2 quiver gauge theory is a conformal field theory. So it flows to a conformal field, and we get a bunch of parameters. For each of the vector multiplets, there's a set of marginal couplings, the complexified gauge couplings that we get for each one of these quiver nodes. So if there's 1, 2, 3, 4, 5, today 6. 6 different gauge couplings that we get to talk about in the particular example I drew, but of course, nothing limits us from much more elaborate or much bigger circular quivers. How would you make an ADS5 dual in this context? You would take a large number of colors. So you take this M to be very, very large, and there's a particular linear combination of the gauge couplings on these nodes, which corresponds to what we would identify with the string theory dilaton, and therefore the cosmological constant. That fixes 1 out of the 6 in this example. There's still 5 remaining degrees of freedom that you get to tune and play with to build a possible ensemble average. Okay. So,
excuse me, this theory is considered to be an effective field theory, right? Correct?
well, so this one here, it's going to flow at long distances to a conformal field theory. But the sense in which it's an effective field theory will be the sense that I'm going to build you an ensemble. And so inside the stringy directions, there's going to be some distance between each of these little realizations of the theory. And that's going to set the effective field theory breakdown scale.
I naively thought instead that it was going to be effective field theory in some expansion in 1/m for large M somehow, but that's apparently not what's happening.
No, and M is going to be, I don't think it's going to break down in M. M as in monopoly or money or anything like that. It's that'll be that won't be where the breakdown occurs.
But for a given quiver, is this exactly soluble theory, soluble CFT?
Yeah. So it's we know that it flows. Well, we have strong evidence that it flows to a CFT because we can just compute when the beta functions for each of the gauge couplings will vanish. That's not too hard of a task. And we can extract even like various scaling dimensions for operators.
And once it gets there, flows to CFT, then we are talking about exactly soluble CFT, or?
I don't know exactly what's meant by exactly soluble in this context.
All correlations are determined, let's say.
Well, in principle, yes, but I don't know how to write down all the correlation functions. So, I was actually toying with the idea of telling you about a different project where we're trying to compute some examples of correlation functions and quivers like this. So it's an open problem to get the full operator content of that CFT and then compute all its correlation functions.
Okay.
So that's not known. But the point is, this thing definitely has an ADS5 dual. That's kind of the point. We have an ADS5 dual, and the key point is that now I have enough leverage to keep the cosmological constant held fixed, which I didn't have in the n=4 Yang-Mills theory example, because the minute I try to make an ensemble over the complexified coupling, I've already messed with the value of the bulk cosmological constant because my dictionary intrudes were too, I didn't have enough flexibility. Okay, so let's build a bunch of examples. What do we do? Well, I don't know how much I should go into the details of this, but from the perspective of F theory, all we're doing is we have a bunch of collapsing curves of self-intersection -2 in the base B, and we just replicate this over and over again. So maybe I'll skip the details. So if you'd like to know more details about this, I'm happy to explain them. But the point is that we can now replicate copies of this, and literally this is going on in this base geometry. So remember in F theory, we work in terms of some 12-dimensional geometry. The shape of the 2 torus tells us about the axiothilaton. And B here is some 2 complex dimensional or 4 real dimensional thing. So we have 4 real dimensions from B, 2 from T2, so that's 6 total. So we're down in 4 dimensions. And what we're doing is we're basically varying the moduli associated to this thing by taking multiple copies. And so we can start building an ensemble as we like for all of the different values of the couplings. So the vector tau here refers to the fact that we have a vector of couplings, not just one, for each of the realizations. And then I can start populating the statistics, my favorite distribution, by just taking whatever profile of number of instances of a particular field theory that I want to talk about. And importantly, I can also keep the ADS radius completely fixed in the gravity dual, because that's just one particular linear combination of this vector tau's entries. Okay, this is just a statement that there's dual realizations of this. D3 branes at an orbifold singularity produce exactly the same quiver. And all we're doing in that picture, so this is again a hypersurface singularity, and we're just saying we can put them at various locations in the geometry. And what we're doing is we're basically taking the same hypersurface singularity, just repeated a bunch of times. And so with the leading order, it just looks like the D3 brane is probing this thing, the same singularity. And there's other dual realizations that allow you to see how we can tune the moduli in these examples. So what is the gravity dual that we build when we do this? Now it looks like for each one of those little pockets where the D3 brane is, we get a holographic dual just based on ADS5 times some x. It's not a 5-sphere anymore because we've done some overfolding. But the point is that we can hold fixed the cosmological constant. And so we really do get like the same throat repeated over and over again. And we get a bunch of disjoint CFTs to leading order that are just cut off from one another. Now, what happens if I start restricting to those operators, the bold O's? I'm not actually able to access the individual motion of each throat. What's happening is there's effectively a collective motion of all the, so in other words, the same particle is being replicated a bunch of times in each of the throats. And when I move one of them, all of them are required to move in unison together. So it's more like a breathing mode that's required to move all together. So from the perspective of this O sector, this bold O sector, it looks as if we just compute all the correlation functions and we play the usual game of ADCFT, it's going to look like a single anti-de Sitter throat instead of a bunch of copies of anti-de Sitter throat. So again, this is because I've restricted my attention to this particular truncated set of operators. So there's the full-blown there's the full-blown set of field theory with all its glory and all that. But then there's this particular subsector inside of that CFT given by the bold O operators. And what we're doing is we're considering just that subsector. The point is, again, that set of operators closes under OPEs to leading order, operator product expansions to leading order. And so it closes as a set of correlation functions that we've been talking about. So I'm allowed to truncate the Hilbert space to leading order to just those operators and say, what would a person who just knows about the bold O operators look to think about the bulk ADS? They're not going to see multiple throats. They're going to see a single ADS throat. Because again, it's this collective motion of every single particle in each ADS throat moving together. Okay.
But what happened to the baby universes then? How did we end up with one ADS space?
Yeah, the reason I ended up with one is because I've done a truncation of the Hilbert space. So that truncation is not UV complete, but at low energies, we can't tell the difference. So the point is that if all I get to talk about is these bold O operators, the only thing I will see is the single ADS throat. But you're absolutely right. If I go to higher energies, okay, then it's going to start breaking up into a bunch of independent ADSs. Okay, so here's the equivalence. It looks like, so again, this is a squiggle. And the reason it's a squiggle is because it only works if I truncate the Hilbert space onto these bold O's. And I can't trust this if I go to sufficiently high energies. It's only a low energy statement. So what's going on? This right-hand picture is precisely the picture that Marolf and Maxfield talk about in their context of saying, let's take the Hartle-Hawking wave function, let's allow the number of boundary components to fluctuate. And what we're doing is basically forming a HET between some fixed number of boundaries and the Hartle-Hawking wave function. This is precisely what they want to claim. So, and then if you follow that, then you wind up talking about particular coherent states built out of those particular choices of boundary values. That's what they call their alpha states, which is the same thing as Coleman's alpha states. So this is the sense in which baby universes reappear from the bottom up point of view. So this statement here is once you accept this, then the rest of it just follows from statements that are already in here. So that's not due to us. But the claim is that, okay, great. This is producing something that at low energies looks like what they wanted. Okay, now here's where the catch occurs. Okay, let's suppose we want to build some macroscopic object, say a black hole, because we're interested in, I don't know, the information paradox, something like it. What would we do to actually start accessing something like the page curve or accessing that? Well, we'd say, well, this thing has a lot of microstates, it has a density matrix and so on. If I really want to reconstruct the page curve, as Paige already pointed out in this paper, you're going to have to sample the associated density matrix a lot of times. And the bigger the object, the more you've got to sample. So if we want to talk about a big macroscopic black hole inside of ADS, we're talking about sampling it a lot. Now, what happens at the level of this boundary CFT? Now we're saying, oh, I'm going to sample, and if you imagine like the radiation getting thrown off, you know, it's almost like pachinko in reverse, I guess. It can pick any of the boundaries to get thrown off to. Once we do that, we have access to sampling what this probability distribution, P of lambda, is. So we're breaking the degeneracy. We're going outside of just the bold O sector. So what's going on? We're trying to approximate that P of lambda, this continuous distribution, in terms of this binned histogram. What are we getting? Well, this is the distinguishability, the sense in which you can tell the difference between the two is calculated by this so-called classical relative entropy. So it's also called the Kullback-Leibler divergence. And in this limit, where we binned it up and made it look pretty good compared to the continuous one, it goes like some 1 over, I'll call it NUV. NUV is, roughly speaking, the number of samples you would have to take or you'd have to draw in order to start telling the difference between the histogram approximation and the actual continuous distribution you want to talk about. The point, though, is that if you let me sample enough times, I can tell the difference, right? Okay, so to avoid anything breaking down, I need to restrict my sampling to something. So if I start sampling and I have a really big black hole, like this is the number of microstates, I can expect a breakdown in the approximation if I ever have to sample even remotely close to exponential the entropy of the black hole. What does this mean? This means that I cannot use this construction to access things I'd like to talk about in terms of the page curve. Now again, what was the point of all this? The point of this was to just generate for you an elaborate counterexample to the claim that I don't need to care about the ultraviolet completion in order to make any of these statements. Well, here I've given you a particularly contrived ultraviolet completion, and oops, I'm sensitive to all the things I thought I wasn't sensitive to. So if I sample this thing enough time, then I'm not able to reconstruct the page curve from this kind of consideration. I just see things breaking down in some violent way. Yes, please.
A little bit more about that, because everything they're doing is really below energy limit.
Right.
And so the only things that are missing in below energy limits are higher order correlates.
Yeah, but it's not quite so simple. This is why I'm calling it an entropic breakdown, because it's true that we're sticking to low frequency modes and things like this, but you're demanding that you can sample a lot of times from the density matrix. I need to be able to do that in order to reconstruct the page curve.
But that shouldn't ever demand that you must be sampling high energy.
No, I'm not saying I can sample at high energy.
Then so if you
So I'm just saying here's a distribution, and I give you this approximation.
yes.
So all we're saying is that, let's say I give you my favorite bin histogram, and I say I want to sample a huge number of times. I can still tell the difference between two distributions if you let me sample enough. That has nothing to do with being at high energies or low energies or whatever. It's just a statement about let me sample this thing a bunch of times. So each time we're going to get out some information.
So both of these, the p-hist and p-cons are essentially effective only at low energy.
Right.
So you're really distinguishing between two low energy systems.
That's right.
And yet you want to attribute the difference to some high energy effect that you ignore. Right? That's the bit I don't understand.
Yeah, so the reason I'm claiming it has to do with the high energy effect is because the best I can ever do is the histogram approximation. I'm never able to actually make the continuous distribution.
So you claim that is effective because it's ignoring high energy.
That's right. So in other words, there's some intrinsic, size to each one of these bins, and I can't get rid of that in the ultraviolet completion I'm telling you about. So even though I thought I was doing a good job building you a good distribution, and I can make this as good as I like, if you sample enough, you can still tell the difference. So that's why I'm claiming this is an entropic or infrared effect, not a ultraviolet effect. Well, not an ultraviolet effect in the sense that we typically use it in effective field theory, saying go to very high energies and compute a scattering magnitude there. You'll see, of course, then you'll see breakdowns of all sorts. This is really a statement about stay at low energy correlations, but what I want you to do is consider low energy correlations with a huge number of, if you like, in and out states. And then at some point you will sample enough to tell the difference.
So what parameters essentially sets the resolution of your video?
Yeah, so that's set by, if you like, the intrinsic tension of the brains themselves. So if we try to go to the supergravity approximation, there's a sense in which we can't really ever say it's localized at this particular point. So there's a delta function approximation that we customarily use it, but that itself is a little bit of a cheat because it has some intrinsic thickness to it. That's what this bin size is being reflected on. So that's why I'm blaming that on a UV effect, even though it sounds like this is a purely infrared thing.
Do I need to worry about the probe approximation as n gets very large?
Which end? This end?
Yeah. Like, I mean, it sounded like you were saying in a sense, as n gets large, I sort of have a very large number of probes in a sense.
That's right. Yeah. So we're always imagining we have a large number of probes, and we're trying to basically carpet the entire set of possible values for the coupling costs. Yeah. Right. So I don't think. Well, the answer is yes. We do need to worry because that's
Okay.
That's exactly what I'm saying. You do need to worry, but you could fool yourself into saying. So if you wanted to, you could take this in one of two ways. You could say, great, you generated the ensemble average you wanted. Let's go to town. But I'm saying, oh, well, I also know exactly where it breaks down, and I can spot two places where it breaks. So you can either be optimistic about what I said or pessimistic. I don't really care which. This is the result. So
normally when you've been data, you know that you made some error in approximating the underlying system.
That's right. That's this thing. So this is calculating the information we would gain if we had switched from kind of the bin diversion to the true, quote unquote, true continuous distribution.
That's local.
Local?
I mean, this is evaluated at each point in lambda space.
Yeah. So what I'm doing is I'm taking like a little step function that's cut off on two sides. So that's why I'm talking about this histogram. And so I say there's like a little constant value on this little bin. And
so the correction is usually related to the width of the bin and the variance of the distribution.
Absolutely, yes. So yes, it depends.
This is effectively evaluating
That's right. So here I just lumped all of that stuff into what I'm defining as 1 over n UV. So you're right. It definitely does. So it goes like width squared, and then it depends a little bit on like the derivatives of the particular distribution, that kind of thing. But I'm lumping all of that into what I'm calling 1 over n UV. So whatever I get, I know that the KL divergence is telling me this is how many samples you need to reliably tell the difference between the two distributions. So yes, if you have a particular continuous distribution in mind, you can definitely work out much more detail about what it is. Yeah. Okay, I'm running a little bit short on time. How long am I allowed to go? Or is it... I'm cutting into my extracurricular activities, right? Okay, but okay, so let me tell you about the lower dimensional examples. So 2D example. So this is another very famous system. So to make this so-called D1, D5 system, we consider, say, type 2D string theory on a 5-dimensional flat space times a circle times a K3 surface. And we wrap D1 branes over here, they fill time. D5 branes wrap the K3 and S1. And if you take the near horizon limit of this, what does this look like? It looks like a black string solution wrapped on the S1. And this famously appeared in the microstate counting of Marolf and Vafa. ADS3CF2T2 goes all the way back to Brown and Hano in the 80s. And it's one of the examples also Melisena talks about. The point for us is that, well, we have some moduli we can vary in terms of the K3. So as we vary the metric moduli in the K3, we're changing the marginal parameters of the 2-dimensional CFT that lives on time and the circle. So what do you think I'm going to do? I'm going to take that modulus and I'm going to start populating examples of it over and over again. So we're not going to have just a single 5-dimensional black hole. We're going to kind of consider a bunch of them spread out in the R4, 1 directions. And we'll try and change the values of the coupling constants locally near each one of these. The reason why I'm going to get away with this is because it's a supersymmetric configuration. And so I'm not going to be too worried about having multiple black holes. There's a no force condition in play that lets me populate them over and over again. Okay, so let's break up the 4 spatial directions into 2 spatial and a complex line. The K3 can be fibered over the complex line so that the total
excuse me, just a quick question. Vafa and Strominger didn't need ensemble averages when they did their computation, right? Entropy.
Correct. Absolutely not.
How did they get, then how would they discovered and noticed that something is missing, if there is something missing? According to you, something is not quite right if you just take this theory on face value.
No, everything's fine. I'm totally fine with this being the end of the story. The question is, how would I reverse engineer an ensemble average?
Reverse engineer.
That's the claim, right? That we're trying to build an ensemble average of 2-dimensional CFTs. So I'm going to try to build that for you. So what I'm going to do is I'm first now giving you a single instance of the 2D CFT, and now I would like to build multiple copies of it.
Okay.
Okay, so let's fiber it. You can do this in such a way that you get the total space to be a Calabi-Yau threefold, and you can sequester these little stacks from each other by moving them around in the R2 direction. Okay, so this allows us to build a probability distribution over a 1 complex dimensional subspace of the full moduli space of K3 metrics. But we cannot actually build the most general probability distribution. So I don't know how to do the thing that, for example, Maloney and Witten wanted to talk about, or Hartman and collaborators wanted to talk about. We can build ensemble averages, but it's a very particular kind. I don't know if it's just a limitation of the model or whether it's something more intrinsic, like it's not actually possible to build what they wanted to do in a unique completion. Okay, when we turn to a 1D example, you can build 4-dimensional black holes by considering Calabi-Yau threefolds of type 2B and wrapping D3 branes on special Lagrangians. So these are 3 manifolds, special kinds of 3 manifolds inside of the Calabi-Yau threefold. You can get a black hole in R31. It usually comes with some electric and magnetic charges, and the near horizon limit just looks like ADS2 times S2. ADS2 being the famous one that shows up in SYK model and also in the Jakiv Teitelboim gravity duel. Okay, so how do we do this? We again take the Calabi-Yau threefold. We vary the moduli of this over the complex line. This builds us a Calabi-Yau fourfold, the non-compact one. This can be done, and we can sequester in just the real line direction. And we can move them further apart than the kind of effective ADS2 radius set by each stack of D3 rings. Okay, so the point is that we can now start building these ADS2 configurations up. A subtlety with this thing is that there's also these so-called ball crossing phenomena, where you start with a particular configuration of known electric and magnetic charge, and as you move through the moduli, it can break up from a single-centered object into a multi-centered object. So if you like, that's telling you that the ADS2 is itself fragmenting into two different pieces, like two different ADS2 throats, and so on. I'm not going to say too much about it. It's either forced on you depending on the distribution you take, or you can avoid it by restricting the places where you want to populate the distribution in the first place. Okay. So I'm basically out of time, and I'm basically done with what I wanted to tell you. So let me just summarize and tell you future directions. So what did I do? I told you about building ensemble averages, probability distributions over couplings via geometry, and its connection to random couplings and holographic. So again, the idea was I built by hand, whatever distribution you want, and then I told you if you truncate the operator's subsector, truncate to these bold O's, it's closed by itself. It breaks down at high energies, but it's fine by itself. And what we're left with is an ensemble average. The thing has a single ADS throat, and you can interpret it in ADCFT as something that would be approximated by a Hawking wave function with some choice of number of boundaries, which is allowed to now fluctuate. What we also saw is that not only is there an ultraviolet breakdown, but there's also an entropic breakdown in the infrared for this thing. And so, at least to my mind, this raises questions about various claims that have been made about using these kinds of constructions to extract, say, page curve or a black hole. Okay, so another kind of technical limitation is that we can't always generate the most general P of lambda. We're usually restricted in terms of what we can do. We actually had the best approximations in the case of four-dimensional CFTs for what it's worth. We can do some examples in two-dimensional CFTs and one-dimensional mechanical systems. And there's some other cases we can also handle. But it's surprising, at least to me, that the best case is actually the high-dimensional case, which is the one I don't think anybody was previously saying we could do at all. Anyway, so that's it, and thanks for your attention.
Yeah, let's thank Jonathan again for this very nice talk. So are there other questions? We had already a few, but from the audience here.
I have a quick one, but I'll wait to see if someone else has any question.
I think the stage is all yours, Ariel.
I'll try to make it very quick. It's a philosophical one, not very technical. At the very beginning, you mentioned that of a puzzle in
Yes.
holography, and then you went from that puzzle to the need for having an ensemble averages and all that stuff, and baby universes coming out of that.
Right.
Now, the question is, could you have arrived at this for the need for the ensemble averages without being aware of that puzzle, but rather from other considerations, like something missing in the description of the bulk theory, or something not quite consistent or not desirable? Is there some other motivation?
Yeah. So one motivation, which is kind of linked to the baby universe one, is that they are just talking about like ADS-CFT with multiple boundaries for the empty de Sitter space. And then the point is that in the gravitational path integral, it looks like there's these so-called wormhole configurations, which would connect the seemingly disconnected boundaries. So that's from the gravity point of view. From the CFT point of view, I think it's a natural question to say, well, this is a perfectly well-defined operation in any CFT. Just take your correlation functions and start disorder averaging them. What does this mean on the gravitational side? That's a perfectly fair question. And you do it all the time in condensed matter systems. Like if you want to talk about spin glasses or things like this, disorder averaging is just part of the game.
I see what you mean, but I was expecting something about landscape philosophy. If you don't do what you're doing, landscape picture has one undesirable feature. You have gazillion, infinitely many possible vacua, and you lose predictive power. You don't know which universe to select. And, wasn't it kind of the motivation was to have some baby universes through which you might be able to choose a low cosmological constant universe, for example?
Well, right. So that was Ullmann's original motivation, or one of his motivations for talking about this alpha states and so on in the first place. Because his point was that, well, let's do this ensemble average over, say, cosmological constant, and we'll see a very small value coming out. Sounds great. I mean, there's all these kind of steps in the actual manipulations of the gravitational path integral, which he kind of admits are a bit
I see.
shaky.
So in summary, the philosophy is still valid, that old philosophy about landscape and choosing a vacuum landscape. But now you have put it in more sophisticated terms, it looks like, right? I mean,
Yeah, well, yeah, yes and no, because I mean, I would say that the ensembles, okay, I would say that what we're doing is a version of his story, but in ADCFT context. I'll leave it at that.
Okay.
So, yeah. But
Okay, thank you. Yeah.
What are the limitations of this kind of effective field theory reasoning? I mean, it's a pretty dangerous thing to just say, I'm going to take like Euclidean gravity and declare it to be like, fine for quantum mechanics. I mean, you can do it, but I mean, I think there's known reasons not to do it, which nowadays are kind of ignored. But okay.
Okay, thank you so much. Thank you.
Thanks for the question.
So is it possible, as one can build a rigorous model as Shankar Stanford S-cube model in 2019 with JT and quantum mechanics? Is it possible to make that rigorous model?
Yeah,
dimensional, because you're claiming that higher dimensional cases are easier.
Right. So the case we got closest to in terms of like JT and so on was this ADS2 times S2 thing. So
like you have the rigorous that rigorous dictionary between Ensemble and ADS.
Well, so what we can do is we can write this thing down, and the point is that there's a quiver quantum mechanics you can write down for each instance of ADS2 times S2. One of the big challenges for a long time is to say, in what sense does this flow to a quote unquote one-dimensional CFT? So in other words, what is the long distance behavior of this thing? You can write down the quiver quantum mechanics, no problem. The question is, in what sense can you reconstruct the bulk ADS2 that you get from it? So if you like, the claim, or one of the claims in SYK is that there's a universality class, so I don't need to tell you too much about what's going on for the CFT1. There's kind of a universality class associated with just these qubits interacting with each other. And once you do the distribution over the couplings, the quartic coupling, you will see something like an ADS2 coming out. So, insofar as the quiver quantum mechanics matches onto that, that's a thing we haven't done, and that's kind of the big open problem, I think, in ADS2 CFT1. Insofar as you can do that, we can match onto that discussion of JT gravity, with the caveat that it's not really ADS2, it's really ADS2 times S2. There are, as far as I know, no known examples of pure ADS with small extra dimensions in any, it's usually like when Rubin type things where it's like ADS times X, where the X is pretty big. So take that for what it's worth. Now the higher dimensional case has a similar feature, right? I claim I can get things like ADS3, ADS5, and so on from a similar starting point. And I seem to have more success in generating my favorite arbitrary distribution in that setting. So here I face the same limitation that there's lots of moduli in the Calabi-Yau threefold that you might want to consider, but I can only kind of cut out one complex dimensional subspace doing this trick. I don't know if this is just because it's a limitation of the way I'm doing it, or whether it's telling me something deeper that I shouldn't expect to get more complicated distributions. So anyway, that's the extent to which I can match to their discussion. I don't know if that answers the.
Okay, very nice, and I'd like to thank Jonathan again.